So the first talk of the conference will be started by Xiaowei Wang from Rutgers, who will tell us about moment map and convex functions.
Okay, so first I wanted to thank the organizer for giving up this opportunity to talk about this work. This is this joint work with Jacob Sturm and Kim Lee. So first I'm going to explain what's the motivation, okay? So motivation is that we look at there's like two types of special metric on a Kähler manifold. So suppose X omega is a Kähler manifold. Okay, then we have two kinds of special metric. One is called extremal metric. So extremal metric says that so the scalar curvature of omega, you take the 1-0 gradient. It's a holomorphic vector field. Okay, so that's the first thing. The second thing is that so-called Kähler-Ricci solidum. Okay, basically says that okay, so suppose you have a Ricci omega minus omega is equal to d bar by d bar lemma, that's equal to d bar theta, and then the 1-0 vector field of theta is maybe I call theta omega is a holomorphic vector field. Okay, so we have these two types of special metric. I mean, in particular, like we have that the KE is a special case of both of the case. So remark is that if omega is KE, then it is both extremal and it is both extremal and the Kähler-Ricci solidum. And in that case, the vector field are all equal to 0. Okay, so in other words, all these vector fields are 0. So now, I mean, for these two type metric, we have a theorem. I mean, the first theorem is due to Calabi. Calabi in the 80s, yeah. He proved that if you have if x omega is extremal, then what you have here is that it's automorphism group. Okay, so I'm going to say the automorphism of x. Okay, I'm going to denote a Lie algebra has a special type. One is you can think of as isometry, complexify plus lambda greater than 0, g lambda. Okay, so yeah, so that's the statement. Where this is the complexification of the isometry group. And well, what is G lambda? The G lambda are the eigenspaces. G lambda is equal to those C lies in order x such that square root minus 1, 1, 0 s is equal to identity, is equal to lambda times identity. So in other words, that's the eigenspace of this operator, okay? Moreover, I mean, you have this eigenvalue is always positive. Okay, so that's a theorem by Calabi in the 80s. Okay, similarly, we have the statement of due to Tian-Zhu in 2000. they have the similar statement. Okay, so if x omega is a Kähler Ricci solid, and then you have the automorphism have the similar decomposition. Okay, is isometry plus direct sum of G lambda. But the only thing, the only difference is that the G lambda is, I'm just going to write down briefly, that's square root minus 1, 1, 0 of this theta omega. So that's the eigenspace of this operator. So then you might be wondering, I mean, what's the reason lie behind both, you know, metric have this kind of decomposition of this such kind of a decomposition. So so that's one of the motivation. The second motivation is that is what we're trying to understand is that suppose you have a symplectic quotient or GIT quotient, okay, with a compact Lie group acting on it, and then we know that the moment map it's a Hamiltonian action. Holomorphic Hamiltonian, say. So this is a Kähler manifold. And I'm going to assume this is rational. So in other words, it's a C1 of a ample line bundle. So the GIT quotient equal to symplectic quotient. Say these two are homomorphic, where G is equal to KC. And now the thing is that you can ask the following question. Okay, so you have a classical moment map, and then you compose with a function, which f is adjoint K invariant. Okay, now you want to ask is that the question will be, okay, the question will be what you can say about the stabilizer. I mean, so in other words,
could you raise the blackboard?
Sure. Sorry. So I'm not going to use that. So suppose that, so F composed of mu D at Z equals 0. What you can say about, what we can say about GZ. Okay, so so the question we want to ask is that try to explain what happens here. I mean, for these two coincidence and what's the reason behind. And the question which related to these two is a following question. Okay, that's the question one. Okay, so so what is the statement? So okay, so first let me state the main theorem first. So our theorem is the following. Okay, suppose that the Z omega is a Kähler. So in other words, you can think of what do you mean by it? I mean, so because the KE problem, CSAK problem, all related to moment map thing, right? So you can think of like solving CSAK metric or KE metric is solving like a moment map equals 0 equation. There, so you can think of like a point lies on the level set of moment map. You can think of it as like KE problem. Then you want to understand what do you mean by a point is Kähler Ricci solid. Okay, so that's kind of related to the question we put above. So we have a Kähler manifold, okay, and suppose K is a holomorphic Hamiltonian. Action. Okay. Then I'm going to define the Lie algebra K is defined to be equal to K plus square root minus 1K. Okay? I intentionally didn't write down the group G because in the situation we're going to apply is that such a G might not exist. Okay? So, but we can write down a Lie algebra like that. So then, this actually is a Hamiltonian, holomorphic Hamiltonian. So it has a moment map, mu mapped to K star. Okay, so mu satisfies the following equation: d mu pairing with cos c is equal to omega sigma z cos c, where cos c is the Lie algebra. Line in the Lie algebra, and sigma z is the infinitesimal action. Oh, sorry, probably this is not a good place to write it. Can everyone see that?
Not much lower.
Oh, okay, maybe. So let me maybe I put the theorem over here. Sorry. So z omega with a say compat, okay, but holomorphic. And with a moment map, satisfy the property that d mu z cos c is equal to omega sigma z cos c, and mu is K equivalent. Okay, so that's because here we have K action, here we have adjoint K star action. Okay, and the sigma z cos c is the infinitesimal action. Okay, so so that's what we have over here, and I'm going to define the Lie algebra G is equal to K plus square root of minus K. So in particular, if K has a complexification, that's the algebra of the complexification of the Lie group, and we define this GZ to be equal to cos C plus square root of minus 1 eta, such that sigma Z cos C plus J sigma Z eta is equal to 0. So in other words, if everything you have a complexification, that's precisely the stabilizer, the Lie algebra stabilizer. But I mean, because I didn't assume the existence of such a group. I mean, this makes sense. Okay, so I just want to put a remark here. If the J, the complex structure J, in particular, this is a Kähler manifold. Okay, right? So a priori, this might not be a Lie algebra, but I wanted to say that J is integral plus that K is a holomorphic. In part, this is the Lie algebra. Meaning that even if this is infinite dimensional or whatsoever, it's a formally Lie algebra. Okay. Okay. Then. Okay. Now, so and suppose that we have a adjoint invariant function. F, okay, which is adjoint invariant. Okay, then what we wanted to say that, and okay, suppose df composed with mu of z equals 0. In other words, we call this kind of point, we call it the extreme point, or you call it critical point. Then what we have here is that the gz we define over there, gz defined over there is equal to kz complexified plus direct sum of g lambda positive. And where g lambda is defined to be those cos C lies in G, cos C lies in G, such that this is compressified guy, square root minus 1, adjoint. Not adjoint, I just say. The eigenspace of this adjoint operator. So adjoint maps GZ to back to self, and it's a self-adjoint operator with the real eigenvalue. Such eigenvalue is positive. Okay, I just wanted to say a little bit about this notation over here. So what we have over here is that F is coming from K star to R, right? So in particular, you have dF, right, lies the due of K star, right? So this guy actually lies in K, right? So that makes perfect sense. We take a adjoint in the Lie algebra. So this lies in the Lie algebra. We want this guy to be eigenspaces. In particular, as a consequence, that's what we already know, that KE is reductive whatsoever, right? If the mole map equal to 0, implies reductive, and one more important is that the critical point or the extreme point enjoys the maximal compact automorphism. So in other words, how to say? So Z is extremal, imply that G, the reductive part is maximized. Right? Okay, so that's what I'm trying to say. So I just want to put a remark is that for arbitrary point, it's very much possible that the KZ is much smaller. Even the GZ is big, but the GZ has a reductive part, the KZ could be 0, okay? KZ could be 0. I just want to say this is not something for free, okay? So this, okay, so that's a first statement, okay? So I wanted to say that actually in the end, at the end of the day, so that explains both theorem, why we have such a situation. In other words, it all follows from this general statement. As long as, one important assumption. F is convex. Okay, F is convex. So what I'm trying to say is that this kind of a decomposition, it follows from some kind of a positivity. The positivity is exactly the convexity here. So, I mean, for example, like, how do we get these two examples? Okay. So I just wanted to give a couple of examples. I mean, classical one. A classical one is that suppose you have this Hamiltonian action, Hamiltonian action. The moment map goes to like a K star, and one F, what we're going to choose Fx is equal to x norm squared. Okay, so that's a classical one. I mean that is used. I mean, like a Kerwan's study of like a cohomology of like a modular space of Jetty quotient. You use this as Morse function, right? So this is clear convex, right? And so in particular, the extremal metric you can think of it's correspond to this function. Okay, and the Calabi-decomposition soliton. Okay, what's a Calabi-decomposition soliton? The Calabi-decomposition soliton. I wanted to say that f of x, it's pretty much like x plus 1 or log x plus 1 plus x, something like that, okay? It's a convex function. We try to check these. So all these kind of things can be put into a unified way, okay? So yeah, so that's, I will explain a little bit more in detail what do you mean by that. But I just wanted to say, these two examples are just basically you choose a special convex function. Any questions? Yes? Oh, okay, sorry. Yeah. Okay, so similarly.
Oh, well, yeah. Maybe you will explain that. I wonder, you mean you can get another proof of Calabi and Tian-Zhu theorem from this picture?
I mean, it's just a consequence of this statement.
Well, that's. Oh, you mean so you applied it?
No, yeah, okay. So I haven't explained. I mean, this. So I intentionally stayed in a way. I didn't distinguish finite dimension from infinite dimension. Yeah, that's what I'm saying.
You just apply it to the Donaldson picture.
Yeah. Oh, okay. Yeah, maybe let me explain the finite dimensional thing a bit more. Then I will go back to how to put this. Okay, so so the next thing you might be wondering, okay, so what about like a Futaki-invariant, right? Futaki-invariant. Okay, so I mean, of course, I mean, different setup you have. The natural question you want to ask. Okay, so in order to talk about Futaki-invariant, I in particular like Tian-Zhu's Futaki-invariant. What's the meaning in this setting? And so let me maybe remind you a bit about some basic fact about. So about the symplectic quotient equal to moment map, right? We have this, and we know mu inverse 0 divided by k homeomorphic to like the GIT quotient of G, right? And so this say this guy corresponds to C1 of L, okay? Okay, so what is Futaki-invariant? Okay, so Futaki-invariant is that basically says that, okay, maybe let me remind you. We say a point lies in ZSS, semi-stable, meaning the inf of GZ of moment map squared is equal to 0. So those Z, such inf of GZ is equal to 0, right? And Z polystable are those Z which mean mu squared is equal to 0, GZ. Okay, so basically to test a point is stable or not, basically we want to say if a point can reach like the moment map equal to 0. So let me draw a picture. So the classical Futaki-invariant can be viewed as the following picture, right? Suppose you have this Z, and suppose this is like a GIT quotient, Z quotient G, and you have a moment map mu go to this is K star, and this is 0, and then you have the level set. You have the level set of mu inverse 0. Now you have orbit. You have different orbits of those G orbit. So you have those G orbit. You can think of this as G orbit. These are G orbit. But some orbit. This is also G orbit. You can think of this is G 0, or maybe you can think of, choose a special point 0. So the point you wanted to say a point is stable or not, basically you take a point over here, and you're asking if along the G orbit, it can hit the level set of a moment map equal to 0. But of course, some of the point that you know, a point if you're unlucky, a point over here, right? Z1, then you know the orbit never touches 0, so these points are unstable. So now the thing is that if you want to find what the obvious obstruction of the point, without going all the way to the level set, but just standing there you wanted to test when it's if there's some obvious obstruction. So what I'm trying to say is that you look at the value of the moment map at that point, and you're pairing with the GZ and goes to C. Okay? So you're just standing there without going all the way to here, and you test this function. And the fact is that this function is kind of like a constant function. So what do you mean by constant? So what I'm saying is that you take, and this guy C lies in GZ, and G lies in G, and you look at this function, okay? Look at this function, and you find this function is independent of G, okay? So you take a point, you look at the parent moment map with the stabilizer, and you found this function is independent of G. So in particular, you know it's an obstruction, right? It's an obstruction because if this point can be moved to the level set, moment map is equal to 0. So it must be 0 at the first place, at here, right? It must be 0 at the first place. So that's I mean, you can think of that. That's the Futaki in the Bailey case, okay? So in our setting, we have a similar invariant, okay? Similar invariant. So I will give I'll give a short proof of this in a minute. But what I'm trying to say, in a setting, if there's a convex function, so what we have over here is that we're looking at the dz mu z minus df check of c and eta. That's going to be our Futaki-invariant. Okay, that's the kind of like the Futaki for the pair, like a moment map with a convex function. Okay, so that's a Futaki for what? So basically, what I'm trying to say is that this is the Futaki-invariant for C. Say to make life simpler, let's assume this guy lies in KZ. So in other words, okay. One statement I forgot to state here is that so if this is a critical point, then I wanted to say you have that df at the mu, which lies in k is actually lies in the stabilizer KZ. So if this is an extreme point, then you have this is true. Okay, this is the case. So if this is the case, so what I'm saying that so you wanted to so what is this this Futaki-invariant to the falling to the obstruction of the falling? Okay, so if z is extremo, so you have like a df at mu is equal to lies in kz, and this guy I'm going to call it kc. Okay, that's pretty much saying, okay, so in other words, it's pretty much saying that df compose mu and kc is equal to 0 at z. That's it. So what is df hat? I have to explain what is df hat. So we have that the k star mapped to r. That's our function f. And since we assume that the f is convex, so we have its Legendre transform. Right? You have its Legendre transform. So Legendre transform maps the k to k star. So these two guys live in the same world. Okay, just want to make sure these two guys live in the same world. So this guy lies in k star. Okay, so in other words, Because C is an extreme vector field. I mean, in the such setting, we have like either extreme vector field or which is solid vector field. If and only if, not if and only if, a necessary condition is this guy equal to 0. Okay, so that's the Futaki. I mean, as a consequence, what I'm trying to say is that Tian-Zhu's invariant is a special case. Okay. Okay, so so now what I'm trying to say is that we have a statement, right? I mean, without a convex function, we know you're pairing the moment map with the stabilizer, you get a necessary obstruction. And here, with a convex function, you try to find a critical point of F composed mu. You also can look at this invariant. Okay, look at this invariant. And also, you wanted to say this invariant, right? Along the orbit, it's constant. Right? So okay, so I just state the fact. Maybe I'm just going to focus on this part of the board. Okay, I will state the corresponding Futaki-invariant fact of a Futaki-invariant. So I just wanted to say a fact is that this guy, mu gz minus df hat adjoin gc adjoin g eta is independent of G. Say, I mean, for simplicity, lies in KZ. So that's Futaki-invariant. Okay. Okay. Now I'm trying to give a short proof. Okay. So how do we prove that? Okay. Why this is true? Okay. Let's start from motivated from say. I mean, the simplest way to see that, if you think everything is projective algebraic geometry, then you see this. You see immediately this is the case. Why? Because if this is projective variety and omega corresponds to some ample line bundle, and L is G linearized, then you know this K. I mean, say the K is because C is rational. Then you know this the GZ. Maybe like a GZ. Basically fix this point. So because of linearization, GZ lifts the action to L. And so what is this guy? This guy is precisely the weight of GZ action on this line bundle, the one-dimensional representation. So, but I mean, this is a local constant function, constructible function. And then you have G orbit, right? It cannot jump. It's integral value. So it cannot jump. So it must be constant. So that's one way to see it. But you might say, okay, GZ might not be reductive. If it's reductive, right, but if it's not reductive, but you will see because the new radical guy have no non-trivial one-dimensional representation, so pretty much you can ignore that. These weights are all 0. So you only care about reductive. So you're done. But I mean, the thing is that, of course, you need a G orbit. You need to have G to help you, right? Does that make sense? The case in our situation, what we wanted to say, we do not have a line bundle and we do not have a G. So we wanted to give a different proof. Okay, so how do we prove that? Okay,
so what are you? So you assume that G, capital G exists?
No, I mean for purely algebraic reason, why this is obvious. Okay, but I mean that's not the proof we want because we want like infinite dimension. We do not have G.
Does the statement make sense? Because you're using little g and capital G.
Here you mean capital G here?
Yeah.
Yeah. But okay. I mean, I'm just explaining the finite dimensional situation, but I'm not gonna prove which is the dimension 3. Okay. So how do we prove this? How do we prove this is that first of all, I wanted to say, I mean. Actually, I gave a proof of this like almost 20 years ago, but it's purely computational. So I want to give a proof with no computation. Okay. So how do you see that? Okay, so what I'm trying to say is that you put in C, okay? So first of all, this C, you like the compressify the algebra, lies in G. And you take D bar of it, and then you have it's a moment map. It's equal to sigma Z C 1, 0 part. Okay, that's almost followed from a definition. The second thing is that you look at the trivial holomorphic vector bundle Z, and you look at this is trivial vector bundle. Okay, trivial vector bundle. Okay, maybe I'm gonna switch to the other board. Yeah. So look at the vector bundle, the trivial vector bundle, holomorphic vector bundle over Z. You look at section. Maybe I'm going to call it section like I call it C. Okay, such that maybe only define over V. V is a subvariety of Z. Okay, it's a subvariety. Satisfying the following, because C is holomorphic. Because C is holomorphic. Of course, this is holomorphic, but now we can talk about holomorphicity. The second thing, we require that the C at the Z lies in V, stays in GZ. Okay? Well, this is an assumption. Then what we have here is that, so then we have the mu Z pairing goes CZ. This pairing, it's a holomorphic function. Okay? But, well, this is complete trivial. Why that? Because D bar mu CZ is equal to D bar hit the first guy. Then by the formula over there, that's equal to mu pairing at the 1, 0 part of the stabilizer plus mu and D bar C. But this guy equal to 0, right? Because this guy is equal to 0. And now by our assumption that the C lies in GZ, so then imply this guy is equal to 0. So we know this guy is a holomorphic function. Does that make sense? So it's a holomorphic function on V. Okay, now we give a proof of, we know why this is a constant. Why this is constant? Because, we learned in complex analysis, right? If a holomorphic function is constant on the real line, it must be constant everywhere. Okay, but the moment map we know, moment map, right, from Z to K, it's adjoint K invariant. Right? On the complex part, it's invariant. So we know must be adjoint G. So that means that implies that this mu GZ adjoint G C is equal to constant. Okay, does that make sense? Okay, So how do we apply to the situation over here? Okay, what is this V? V just adjoint G orbit of Z. Okay? In particular, finite dimensional situation. But in general, all we need is that the V to be like a complex summary, which is the case when we apply to the infinite dimensional setting. Okay, so that explains this is the classical part. Now, what about the df hat part? The df hat part, we also, so I wanted to say this guy is constantly independent of G, right? Independent of G. So we have this part independent, right? This part independent. What about this part? But this part, it's actually easier. Why? Because f is a function of f is adjoint invariant, right? You might think f is a polynomial. So F lies in what? Lies in C, oh no, lies in R, K, adjoin, right? Adjoin, man. This K is not field, it's K is the algebra, okay? So, but this guy is actually have it's equal to what? It's by Chevalier, right? That's equal to adjoin G. Restrict to the real locus, right? Right? And all of these equal to what? Equal to this guy is equal to what? This guy is equal to C at the maximum tori. And Y group invariant. Further, which I'm toward the end, I'm going to mention it, but that's exactly the cohomological ring of VG. Right? Okay. So you know this function have a natural extension, which is adjoin G met. So this adjoin K is actually, okay, let me give an example. Okay, let me give an example. Give an example is like, suppose A is like a matrix, like a GL. Okay, maybe lies a unitary group. Then we know that the trace AA star it's a K invariant function, right? It's adjoin K invariant function. It's an adjoin K invariant function. Adjoin U invariant. Right? But what is this guy? This guy is actually the restriction of adjoin minus K squared. Restricted unitary group. Does that make sense? So this is the guy lying here, okay? So this guy is what? This guy is adjoin G. Okay, this is adjoin K. Okay? So then, I mean, because F is adjoin G invariant. Exercise, you find DF is adjoin G equivalent. Okay, so I mean, we put these two parts together, so you get this is invariant. Yeah, this is invariant. Okay. Okay, so now I'm going to talk about these its application to the statement at the very beginning. So given a simple manifold, right? And it was Donaldson and Fujiki introduced the following space, right? So-called integrable omega compatible complex structure. So those are J lies in the anamorphism of Tx gamma satisfy omega J dot is equal to omega, and omega J dot is positive. And now we know this is kind of like infinite dimensional Kähler manifold. And it has like a 2 Kähler form, okay, actually. At least we know there's 2 Kähler form. One is like a Mabuchi or Fujiki or Sam's, right? And basically, okay, so where does the Kähler structure come from? I mean, you can think of the Tormo. I mean, the simplest way to see that is that you can think of this guy is like locally, it's like a mapping space from R2n to SP to n over U. Okay, and this guy is what? This guy is bounded bounded emission symmetric domain. So bounded emission symmetric domain, then what you have here is that you have a natural Kähler form. And you know the mapping space, as long as you have a volume form on the domain, the mapping space, you pull back all the structure over there. It is Kähler complex manifold. Your mapping space is Kähler complex manifold. So that gives a Kähler. So you get the Kähler form from here. And for that, we know that Hamiltonian group, right? Hamiltonian group acting on J. Hamiltonian of X omega acting on J give a moment map. Moment map is to the top form. Top form of X. And the moment map is given by J goes to the Riemannian scalar curvature minus S bar times omega n. Okay, so that's one symplectic form, Kähler form. Another Kähler form is actually yeah. So was actually followed from Bobenson's positivity of the direct image sheaf, and I'm not gonna. So another Kähler form, maybe I call it following Donaldson, we call it Branson's Kähler form. Kähler form, and again, a Hamiltonian group acting on it. And Hamiltonian group acting on it. And what is the moment map? The moment map, again, top form. J goes to, maybe I call it Hj. E to the Hj minus 1. Okay. So what is the e to the Hj minus 1? Times omega. Hj is the Ricci potential. Omega minus omega. So maybe Ricci j omega is equal to d bar j, dj d bar j hj. Okay, so yeah, so we're going to apply our setup to this situation. So this situation is that the first case you just take f of x equal to x squared, and then what you have here is that the scalar curvature squared. That's moment map squared. That's corresponding moment map squared, and the critical point gives you the extreme metric.
You substitute some function of x to the small x, right?
Say it again.
You substitute. So small f is a function on the algebra of Hamiltonian.
Small.
So I mean, you
yeah.
substitute some function on large x to small x.
What do you mean large x?
Large x is a symplectic point.
Yeah, this is gonna be our z, because our setup is everything z, right?
So well, if you write small fx, so.
Oh, okay. Yeah. I mean, well, that's good. Okay, yeah. To be more precise, it's a functional. That's right. Actually, basically, it's gonna from ham. Like, okay. So it's okay, C infinity of Ham. Integral is equal to 0. It should be functional to R. And the functional in our situation is basically F, or maybe I call it phi, goes to E squared. Okay? Yeah, that's right. Okay, the thing all I'm writing down is actually the integral kernel. Okay? But interesting thing enough, in our setting, the Legendre transform of the functional is the Legendre transform of the kernel. Does that make sense? Okay, so in our situation, it's happened to be integral commuted with the Legendre transform. Okay, so yeah. So a priori, I need to do the Legendre transform of this functional, right? In our setting. But the Legendre transform of the functional is equal to the integral of the Legendre transform of the kernel. Okay? This is true, okay? In our situation. But what I'm saying, okay, so this is this case, and in that case, F again, I'm going to write on the kernel is x plus 1, which is in Donaldson's Dean functional paper, something like that. Yeah, something like that. And you get exactly you get the so in other words, what we have here is that both Calabi-decomposition and the extremal metric are extremal point. They are all extreme point in the same setting. Okay, so that kind of like answer the first motivating question. Now the second thing, there's some technical thing I want to address over here, which is infinite dimensional, finite dimensional situation. Okay, so what's the most problematic thing here? So pretty much everything goes through. I mean, even like the proof of a Futaki-invariant whatsoever all go through because I didn't really use it's being finite dimensional or the existence of G. Okay, as long as we know the leaf, right? I mean, although we do not have a Ham C, we do not have a Ham C, but we do have a Ham C orbit, right? This guy exists. This guy exists. And this already enough because the proof is, if you remember, I just need a complex subwriting. Does that make sense? So this is okay. But there's one important issue which is not coming for free is that this fact. We do not have a Xiaowei for infinite dimensional guy, right? I mean, because the thing is that Xiaowei said that you have this function, you have like a G extension, right? Like the situation over here, such as adjoint G invariant. But in our situation, we don't even have a G, let alone but the adjoint G orbit, right? So we do not have that one. So how do we replace this Xiaowei stuff? So I just wanted to say the following. Okay. So we have Ham x omega, and the Lie algebra is Ham x omega. Loosely speaking, it's a space of function, right? C infinity of x. And now the question is, of course, you can complexify it, right? You can complexify to C. Now the question is that taken a phi lies in it. What do you mean by adjoint Ham C? What is the adjoint orbit of that guy? Right? We do not have that one. But the thing is that luckily, we cannot take the adjoint orbit of the whole thing, the whole Lie algebra. I mean, a priori, that's the key difference between infinite dimensional and finite dimensional. Infinite dimensional or finite dimensional, this has nothing to do with the space Z we're acting on, right? I mean, it's a purely Lie algebra question about the Lie group. I mean, Z and the Lie group are completely independent world, right? Completely independent world. But here, we need our Z to help us to construct this guy. So in other words, is that we're going to use, okay, so what I'm trying to say is that if, so theta C lies in Ham, okay, or C infinity of Ham of x omega, such that this function coming from automorphism. So in other words, so C is you can think of this as a holomorphic vector field on x omega, okay? and this lead derivative of j is equal to 0, and this j is integrable. This j is integrable. Then we are able to say these adjoint orbit do exist. Okay, we have a adjoint orbit. So in other words, I wanted to say this guy do make sense. This is a function, okay. This guy do make sense, and by that, okay, because of this, then we found that any function, so you think of f as a polynomial, you integral, okay, f, you think of f probably is convex, f is C infinity. One variable, okay, maybe it's even easier, you think of just a polynomial. And you compose theta, and then omega to the n. And this is a function of theta. Okay. And then you find that okay. So for example, okay, let me again draw the analogy between finite dimension. Okay. So the finite dimensional thing, actually, in the proof of like a Futaki-invariant, what we essentially use is the following. So given a Lie algebra, right? Given a Lie algebra, and then you have it's so-called a polynomial. You have a polynomial Poisson algebra, okay? The polynomial. I mean, naturally. I mean, it's canonically. And you have a Poisson structure as well. And then suppose you have any function goes from this guy to C as a Lie algebra homomorphism. Then you will see Lie algebra homomorphism. Then you will see X composed with any phi, okay? Yeah, phi of C. This function will be adjoint invariant. Adjoint action, you can think of this as like a universal Hamiltonian algebra. You have adjoint action on it, and you take a derivative. Okay, so this guy. Yeah, you think of this guy. This guy, suppose in the is a polynomial inside G, a function. Then this is adjoint invariant. And the reason is fairly simple. Okay. So maybe just 1 minute. So the reason fairly simple because X, you take a adjoint action e to the t eta C and ddt. Because this is the algebra homomorphism, it's linear, so it's equal to ddt chi phi prime and phi prime of C and eta C. Okay, but this guy is equal to eta phi C. Here you use that the Lie bracket is a derivation. Okay, it's a derivation. So this is equal to 0 because it's the Lie algebra homomorphism. Lie algebra homomorphism. So this guy, I mean, this is abelian, so this is equal to 0. So this is gone. So this is equal to 0. So I mean, as a consequence of this fact, we know that this kind of functional is adjoint G-man. Okay, adjoint G-man. Because the reason is that okay, I just wanted to say you look at its complex phi orbit ddt is equal to the Poisson bracket with something. Okay, so it's adjoint action. It's infinitesimal adjoint action. So this is true. Okay, probably the last word I just wanted to say because I explained this one thing. So you can think of like a Hamiltonian situation to define norm on the mapping stack to theta, he chose H4 of the Artin stack, or the H4 coming from BG, right?
Sorry, we can't do this.
Oh, sorry. Yeah. So, I mean, basically, you want to do. Suppose you have a global quotient, and Hamiltonian need to choose a B class in here, or even like a B, because X maps to BG. You take H4 of BG, take a quadratic guy as a norm, right? Okay. So you can think of this quadratic guy as a constant metric on the space of norm. But our function f is actually a non-constant metric because, I mean, this is a quadratic term. You take the Hessian, it's become a constant metric. But our f is basically, convex function. You basically take a non-constant metric on the space. Yeah, so yeah, just you can think of, I mean, that's, the f introduced a kind of like a non-constant norm on the space of the algebra whatsoever. Yeah. Okay. So I'll stop here. Thank you.
So questions?
Yeah. So I mean, if you apply your Futaki-invariant with f.
Yeah.
To like the extremal setting.
Yeah.
So yeah, if you have an extremal.
Oh, okay, yeah. It's a special case of this because what is extremal? Extremal case basically says this guy lies in KZ, right?
Yes.
Okay, but that's another way of writing is that another way of writing of the mu x minus kc eta for any eta equal to 0, right? I mean, okay, why is that? Because x squared derivative. df is just x, just identity. So in particular, it's a special case.
And one of the other points where convexity comes in is when you're proving uniqueness of the external vector field.
Exactly. So yeah, that's a good point. I mean, the thing I think for all the various kind of generalization of like solid stability, you only need positivity. But as long as you touch the uniqueness, convexity, positivity, you need that one. So yeah.
Chris, any more questions? If not, let's thank Xiaowei again.